Okay, hopefully this is recording correctly, but I'm going to go case by case through the 4 different changes that we talked about in the intro part of the presentation here. And we're going to go through and take like an actual look at an equilibrium process and what is going to be the LeChatelier effect of doing various things here. So here's case 1, right, where we talked about the fact that one way to affect an equilibrium position is to either change the concentration, or the same way of saying that in a gas phase reaction is to change the partial pressure directly of a reactant or a product, right? So imagine that I have some sort of process at equilibrium, right? And then this process at equilibrium, I think, is directly from the recitation here. So we all know, based on our recitation, right, I gave you some sort of problem where you determine the equilibrium concentration of all 3 of the species that are involved, right? This one product, and then we have, of course, these 2 reactants. And so let's say that I have this thing already at equilibrium and I want to make a change to it somehow, right? I want to, let's say, increase the amount of SO2, right? So what I'm saying is that I'm going to find the reaction vessel. I'm going to get a tank of SO2 and I'm going to start trying to increase the amount of this. And a pretty, I won't say odd thing, it's actually kind of expected if you think about the fact that you have to maintain the equilibrium constant at all costs here. What's going to happen is as I increase the amount of SO2, what happens is I'm going to do what's called a shift to the left, right? And that's the way that a chemist would typically talk about it. Anything you do to increase the amount of something on the right side or the product side is automatically going to produce more reactant, right? And so we would say that increasing SO2 is going to tend to shift equilibrium to the left or towards products, either way that you want to say it. Right? It turns out the exact opposite would happen if I somehow had the ability to reach in and remove SO2, right? And there are, ways of ways of maybe like scrubbing a system of SO2 and things like that. So you can actually remove this thing from equilibrium, and it turns out, well, if you add something and it shifts equilibrium to the left, the act of actually removing it is going to do the exact opposite, right? It would actually shift it to the right in that case. If I were to take the amount of SO2 and I decreased that amount, right, that's going to tend to decrease the amount of SO3, which is the same thing as me saying that I have shifted equilibrium over to the right. Just spell right. There we go. And so it's pretty easy to kind of understand, well, if I increase something, it kind of shifts away from it. Honestly, the harder part for students a lot of times is what happens if you remove it from the system. Well, what I do in each of those cases, I think, well, what would happen if I increased it and then I do the exact opposite, right? So the interesting thing is that O2 kind of gets taken along for the ride, right? And so in this particular case where I'm decreasing, I'm externally trying to take out SO2 from the reaction, and I see this shift to the right, what that means is obviously my amount of SO3, like we just said, is going to go down, right? So decreased amount of SO3. The O2 kind of gets taken along for the ride, right? And so you actually end up, if you decrease the amount of SO2, you're actually going to shift equilibrium to the right, meaning that your amount of O2 is actually going to go up, right? And so this is kind of the way that chemistry often makes us feel is that anything you try to do in it, it kind of does the exact opposite of what you would like to do, right? So in this case, right, this idea of LeChatelier is truly that anything you do to one of the products of the reactants in the system is going to tend to shift the equilibrium away from the effects of whatever change you tried to make. And so one thing I did want to mention is that we are going to see things this term where we can actually affect the equilibrium process here. We can end up with LeChatelier effects by actually either adding or removing some pretty unusual things that don't at first glance appear to be part of the reaction. In this particular reaction, that's not a great example of that. So let me show you an example of where we have to be a little bit careful in trying to judge the effect of some sort of change in concentration here. So a good example of this issue that I'm talking about here happens when you're talking about some sort of solubility equilibria. So I have an equilibrium process here, which is really just the dissolution of calcium carbonate, right? And so like if you imagine having solid calcium carbonate and you try to dissolve that in some sort of water, what you're really waiting for when that thing dissolves is that dissociation that we know that ionic compounds have to do into the Ca2 plus aqueous ion and then the carbonate aqueous ion that you can see over here on the right side. Well, as you might expect, if I were to take some sort of compound, right? Let's say, I don't know, let's take some sort of calcium salt that is soluble, right? Let's say I've got calcium nitrate, right? Well, it turns out that if I were to take some sort of calcium nitrate solution and add it to this thing, it turns out that really what I'm adding, because calcium nitrate is completely soluble, it's really adding a whole bunch of calcium 2 plus ions, right? And so this is a great example of where LeChatelier is going to come into play, right? If you try to add some sort of common ion, this is called the common ion effect. If you add some sort of common ion, in this case calcium 2 plus, you're going to see a shift in equilibrium, right? You're going to actually see, just like we saw before, if you try to affect one side of the equilibrium, you're going to tend to shift the equilibrium away from the effects of that change, right? So here's a great example. This one's pretty straightforward, right? I try to add calcium 2 plus. Oh, oops, I'm going to go ahead and form more of my calcium carbonate solid in that case because I have shifted the equilibrium away, right? So I'm going to form more calcium carbonate. You can probably figure out that, in fact, if I add calcium nitrate to this thing and I'm adding more calcium 2 plus to the system, well, that's going to tend to decrease the amount of carbonate that I have, right? And it kind of makes sense. Like that's what it means when you're actually shifting equilibrium to the left. You're saying that more of these things are going to form calcium carbonates. In order to do that, you actually do have to consume a little bit of your carbonate, right? And so, again, this is LeChatelier's principle. Anything you do to try to screw with a reaction is going to do the exact opposite. And of course, like you can actually use this in effective ways. A more difficult effect having to do with LeChatelier would actually be the following, right? Instead of adding calcium nitrate as a source of calcium 2 plus, what if I went ahead and added what appears to be like a completely unrelated compound, right? Let's say that I just add a whole bunch of HCl, right? Well, it turns out what happens is the second that this carbonate comes in contact with HCl, and you may or not remember this back when we were talking about acid-base chemistry, well, that's essentially going to react with this CO3 2 minus through the following reaction, right? CO3 2 minus in the presence of HCl will actually initially have us form H2CO3 plus, just a Cl minus over here. And this thing tends to degrade itself into both water and carbon dioxide, right? And so we've all seen the volcano that you can make from baking soda and an acid, that's essentially what you're doing here. If you add HCl to this thing, the whole point of this reaction is that you're actually decreasing the amount of CO2 2-, right? So how do you think the reaction would be affected? Well, if you try to decrease the amount of this thing, you're probably going to need to have a shift to the right in equilibrium, meaning that you'll actually consume a whole bunch more of this calcium carbonate in order to kind of replenish your stock of this guy, right? And so it's kind of like there are a lot of these changes which are not entirely obvious, that do take a little bit of practice to find, and that's certainly what we're going to be doing this term, is doing some of these more kind of indirect changes to equilibria like this. So let's go on to the very next case. All right, so now we're going to go on to case 2, and we're going to change temperature for an equilibrium reaction. Specifically, I'm going to highlight what happens in an endothermic reaction, and then we'll go through kind of like part B, where we look at what happens in an exothermic reaction. The key to kind of understanding this is that, first of all, let's just pick out an endothermic reaction that I just randomly found on the web here. So if I want to form NO gas, I could do so using this equilibrium process. And it says that my enthalpy in this particular case is about 180 kilojoules per mole. Right? So we've got an endothermic reaction, and what that means is that anytime you see a positive, right, that means that you actually have to input heat into the reaction. So what I'm going to do is something that is technically not correct, but definitely helps us to understand the effect of the LeChatelier effects that we're going to have to think about, right? So typically an endothermic reaction, if you think about heat as being on the reactant side, that is going to allow you to do a very similar analysis as what we did in that very first case where we changed the concentration of something. Well, it turns out if I change the temperature and I increase the amount of temperature, right, increase the amount of heat on an endothermic reaction, that's of course going to tend to counteract, or LeChatelier's principle will counteract that effect, and it'll say, well, what I'm going to do is I'm going to shift to the right, right? And so in an endothermic reaction, if you increase the heat, there is an overall shift of equilibrium position to the right, or in other words, towards products, right? What does that mean? Well, it means your N2 concentration is going to go down. It means your O2 concentration is going to go down. Your NO concentration is going to go up. That's what the shift to the right actually means. And I will say probably the one thing that confuses students the most is if you make a reaction cooler, right? That is the exact opposite of making it hotter, right? And so if I think about what has to happen for an endothermic, if I increase the amount of thermal energy in there and I get a decrease in N2 and a decrease in O2 and an increase in NO gas, well, obviously, if I do the exact opposite, right? In other words, if I decrease the amount of heat by lowering the temperature, what's going to happen is the exact opposite, right? We're going to end up with a shift to the left. Right? Or towards reactants. Again, right, just to beat that dead horse, a shift to the left, what that actually means is that I'm going to have a decrease in NO concentration. I'm going to have an increase in O2 and N2 concentration. And so in much the same way that we talked about case 1, you can treat heat much like a reactant in an endothermic reaction. So now let's see how this kind of changes for an exothermic reaction. So here's another random reaction I found off the internet that is an equilibrium process that we know to be exothermic, right? So keep in mind, if we've got a negative sign, that means that we're going to be releasing heat to the surroundings. So let's do the same thing we did before, right? Well, if we're releasing heat to the surroundings, that means that we can essentially think about the heat being released as a product. And so if you were to, let's say, increase the temperature of one of these reactions, what's going to happen is exactly what we would expect, right? We're increasing the amount of heat. That means that overall, we're going to see an overall shift to the left, or shift towards reactants. And the way that all of these concentrations or partial pressures are going to be affected is probably pretty obvious by now. If you shift to the left, that means that I have to decrease the amount of that, and I'm going to increase the amount of Cl2 and also phosphorus trichloride. And again, right, if you are ever asked what happens when I cool down an exothermic reaction in terms of LeChatelier shift, it is much easier to first think about what happens when you increase the amount of heat in something and then do the exact opposite, right? So obviously, if I cool this reaction down, there's going to be a shift towards products, right, and shift to the right. Okay, so let's go to what really is our last case. Okay, so here's our last case, and that's the effect of changing volume. You might notice from the very beginning, the introduction, I did mention the effect of changing the partial pressure of something. We kind of handled that when we went through the LeChatelier case 1. So really that very first case kind of covers two of the things that were presented earlier. The effect of changing volume, the good news is the only place that this has any role whatsoever is if you're specifically in a gas phase type equilibria. If this is some sort of like aqueous equilibria, there is no real way to change the volume of the container. And so in the case of a gas, right, those things being compressible fluids, that allows us to actually affect an equilibrium potentially, right? And so the key to understanding the effect of changing the volume of container, the first thing you have to do is, first of all, check that it's a gas phase type reaction, which this one is a gas phase equilibrium. And what we're going to do is we're going to look at the left side, and we're going to count up the gaseous moles of reactant on that left side there. So in this case, I can see that there are 2 total moles of gaseous reactant on that side, and I can see that there is only 1 mole of gaseous reaction over on this side. It turns out that if you were going to change the volume of a container, is that the side with more moles of gas, right? And so this is the side with more moles of gas. This will tend to be favored at larger volumes. Okay, so that side is going to be favored at larger volumes. Obviously, the 1 mole side, if you try to make the volume very, 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 very small, it's going to tend to shift to the other side, right? And so, for instance, you might see some sort of question sometime where we say that, like I've got an equilibrium established, I'm in a 1 liter vessel. Which direction does this equilibrium change or shift if I were to, let's say, half the volume of the container, right? Well, in that case, if I make the volume of the container smaller, that means that I am going to shift in the side that has less gaseous reactant, right? And so in that particular case, we would see an overall shift to the right in equilibrium towards products, right? Because there's only 1 mole there, as opposed to there being way too much crowdedness at the end. On the 2 mole side, the equilibrium will kind of try to shift over. Obviously, if we had some sort of other reaction, which I guess is probably a good time to talk about another reaction where, let's say, you have a whole bunch more moles of gas on one side than the other, the exact opposite is going to be seen, right? So like if, let's just do it. All right, so here's another typical type of LeChatelier question here, where it says something about, I have this process at equilibrium, which is the reverse of the Haber process that we talked about in a previous lecture. How is equilibrium affected if the volume decreases by 3 times, right? Well, like always, what we're going to do is we're going to determine the amount of gaseous reactant on both sides, right? And so this one has a total of 4 moles of gas. This reactant side has a total of 2 moles of gas. And what I like to do is just kind of make a little note that tells myself, okay, well, if I've got a really, really crowded side, right? So this side is going to be favored at high volumes, right? There's just something about a bigger number that it makes a lot more sense that if I do everything according to like a high volume, right? So 4 moles definitely going to be favored at high moles or high volumes, and then the opposite is true. The reactant side is going to be favored at lower volumes. Well, if you look at the question, how is equilibrium effective if the volume decreases? Well, that means obviously the volume got smaller, right? And so I am going to tend to see a shift to the left in that case, right? And because that left side is going to be favored at smaller volumes. So that's LeChatelier's principle, something that we're going to be applying a whole bunch of different ways throughout the term. Certainly this is going to come to play when we start to talk about acid-base chemistry in the next couple of weeks. So certainly something that you should understand. And if you need any other resources or you need to talk to me about it, I will be around. So I will talk to you soon.